Okay, so to start with understanding on the double integral, so what is the double integral in general looks like? So we have the double integral of the two variable function where there is dA and then there is r there. Okay, so as I mentioned before, so this is the integrand, so we call this as integrand, and so this is called integrand, and this is called order of integration, and the r here stands for region. So how can we explain the double integral in language? So we are evaluating the double integral of the function f over the region R. Okay, and here the order of integration is just dA in general. Okay, so firstly, I want to introduce you first what is region mean, R. Okay, so here we can say that this is a double integral, or you can see there are two types of double integral where we have dx dy or dy dx, and these are evaluated over a closed bounded region in the xy plane, which means that the region are lying on the xy plane. Okay, so in this case, the idea is what is actually happened here. So where is your function? So this is your f. So your function is in general, or in more general way. So we have a surface. So now we have a surface green, this green surface. Okay, so now we want to compute the double integral of this green surface, not for all over the green area of the surface, but only over this particular area, which is we call that as a region. So we want to compute the double integral of this function over the region R. So in this case, you must have the information about the region. Okay, so what is actually region? So since the region here is lying, okay, the thing that we are discussing now, we have a function of xy plane. I mean, in terms of x and y. So meaning that the region must be lying on xy plane. Okay. So what is actually the shape that you can see about the region? So actually the region is the shape on 2D, the curve on 2D that you can see from Z here when you are standing over here. So when you're looking down, so you can see this just like triangle shape, right? But it's not necessarily triangle. It can be any kind of region. Okay, where in general we call that as there are two types of region: rectangular region and non-rectangular region. So that is about the R. Okay. So now the R here will determine your limit. Okay. So then because of now you have something in terms of x and you have something in terms of y. So which one will be the first or which one will be the second? So it depends on the order of integration that you choose. Okay. So how can you determine the order of integration here? Depend on the shape of the region or the function of the region that you can have. Okay. So now let's okay, now we now I already introduced you what is R mean, which is the region over here in blue one here. And then now we are talking about dA. So since we have a double integral and we have the function in terms of x and y, so meaning that your order of integration, there are two options, whether you have dx dy or you can have dy dx. So meaning that if you put the order in this form into this double integral, so it's become f, the function of, so let's say I'm choosing the first, so dx dy over the region R, where your R is on xy plane. Okay, so in this case, why do we need to put the xy here? Actually, you don't need to put, but just to let you know, so it is possible, just to let you know that your region should be lying on xy plane. Okay, or you can also, if you choose the other type of order of integration, so you can rewrite your double integral to be dy dx over the same region. Okay, so let's say you have the same integrand, this one and this one, and also you are having, when you want to compute this, you are having the same region, so you have exactly the same shape of region on the xy plane. So the result of using dx dy and using dy dx, they will be the same. Okay, so this result will be the same as this, but the difference is only your order of integration. Okay, so how can if you have fx and then y, this is about differentiation that we have discussed last time. If we have fxy, meaning that we first differentiate f respect to x, and you will get the answer, right? Something expression, and you then after that you differentiate respect to y. So that is the process. You do the differentiation process part by part. Start with x and then y. Or you can have fyx, which means that you do the differentiation respect to y first, and using the latest result, you differentiate respect to x. So how about integration? So how do you know which variable variable comes first? So you have to look at the order here, dx dy, which mean that the thing that you are doing is, okay, I just erase the circle first. So you are actually settle down for this integration first. That is called inner integration. You settle down, I mean you first integrate the integrand here, the function given here, with respect to x. Okay, and then there must be a limit. So then you need to put the limit. So when you put the limit, so you will get some expression. Okay, in this case, after you substitute the limit, it's not necessary you will always get a function. Okay, but you can have an expression, but still, if you have first, you have to integrate respect to x first. So meaning that after you substitute the value, so there is no more x. The only expression left can be constant or can be in terms of only y. So there is no x because you already replace the x by using the limit that you have. Okay, and for that I will explain in details later when we have the example. Okay, and after you're done integrating respect to x, so next, whatever answer that you obtain, we have to integrate respect to y. So that is the second integration. So, and after that, you replace the value of y using the limit that you have, and finally your final answer should be a constant. Okay, because we use the same understanding as the I mentioned earlier, that when you have when you want to integrate and there is a limit, so your final answer should be a constant. So now, by extending that understanding into double integral, so once your double integral there is a limit, your final answer here should be constant or value. Okay, and then for this one, so the same, you integrate first with respect to y. and then you substitute the value of y, and you will get the expression can be only constant or in terms of only x. So no more y, because the y is already replaced by the value that you have. Okay. So after you obtain the value, then we integrate with respect to x, and then you replace the value of x, and finally your answer here should be constant. Okay, so that is the process, the step about the double integral. So that is about the region. Okay, if a single integral where we have a single variable respect to x from 1 to 2, so let's say there is a limit there, and you will get, let's say, 2. So how can you interpret this? What is the actually you are doing? So this one is called area. We call this as area under the curve or below the curve, right? For this one. But now what is the physical meaning of double integral? We have dA and over the region. Okay, for your information, this one is actually what, okay, if I'm asking you, and what are you doing, what is the thing that you can obtain from double integral? So you might wonder, right, what is something, how can you, okay, you know how to solve the double integral, then what does that mean? Okay, so this one is actually you are computing the volume. You are computing the volume. So I would say that what is the application of double integral? So you can use double integral to evaluate the volume of y. Okay, so that's the thing I want to explain to you. So as we know that this one is the value of z, because we know that z is given by the function of xy. So this is the value of z. Okay, and this one is actually why we put a. Actually, there is a reason why we put a. A is actually stand for area, luas, area. Okay, area of what? Area of the region that you have here. The area of the region. So this is area. And this one, I would say this is just like height of what? Okay, look again this diagram, but then I sketch here. Okay, so the green one, so the green surface is the surface of the integral here, where let's say okay, I should transfer over here, just a second. Okay, so just look at here. So we are talking about double integral. So we have double integral of the function dA over the region. So as I mentioned before, dA here is area. Okay, so as I mentioned earlier, what is dA? dA is actually the order of integration, where it will give you dx dy or dy dx. So how can you have area from dx dy? It's just like you multiply the changes of x and multiply by the changes of y. Or if you have this, so you multiply the changes of y and the changes of x. So where is the changes comes from? Okay, since we are talking about, we want to evaluate the double integral of the given function f of xy over some over the region. So that is the region. So let's say I redraw that. So that is the region. So let's say we assume now, just to get understanding, we assume that we have a rectangular region. So as you can see here, so this one is the changes along x, because we have x is 0, while this one, the length here, is the changes of y. So for the changes of x, we put dx, and the changes of y, we put dy. So what is the area? So what is the area for this region? So that is your region, right? So the area of the region is just like x multiplied by y, but now because we have a very small changes, so we just put dA is given by dx and multiplied by dy. So that's why we say that this one is just like the area of region. So that is our dA. Okay, so as I mentioned before, this one is the value of z, which is where is z. So z is whatever value lying on the surface, isn't it? For whatever point that you choose in the region, for whatever point that you choose in the region, so you will always get the value of z somewhere here, which is on the surface. So let's say, okay, I choose another, let's say this one. So I put one point, I just select one point in the region, so then it will give me the z somewhere here on the surface. So similarly, if I choose another point over here, and then you will get the value of z over the surface. So and we can assume that this one is just like the height, right? What is the height? The height is the length from the something on the lying on the floor to the surface. So we call this as just like the height, which is z, value of z. So if we go back with the double integral here, when you have the height, so this one is considered the height and multiplied by the area, and you can get the, so the answer here is volume. Volume of what? Volume of this solid, the blue solid here. So because how can we get this blue solid? So actually, if we go back to our surface here, just now we are talking that we are integrating the double integral of the function dA over the region, where the region lying on xy plane. So we split the region here into a very small rectangle. So this is the original one. So we just split them into a very small rectangle. So we just pick one very small square there, and then when you resketch, so you will get just like a cuboid. Just you do a trace, right? And this one, so you can have something very small. So I don't have the ruler, but will try my best to sketch. So there is a line. So this one, and then this one. Okay, and then I have, no, sorry. Okay, and then there is something at the back. Something at the back, and then 1, 2, 3, and the last one. Maybe I need to resketch the triangle here. Okay, so that is a square. Okay, so imagine when you have a very small rectangle for dx and dy, and actually you have a very many this kind of solid. So we call this as a parallelepiped. So I'm not sure whether it is okay. It's actually been shown here. Okay, so you can see that on the next slide. Okay, so this one. So actually, this one is just one parallelepiped, one parallelepiped. But actually, this one is coming from the combination of very many parallelepiped, which is part of the surface and the region. So when you have the very many parallelepiped and you total up the volume, so it's something related to the limit, but we don't discuss that one. We just assume that the double integral is actually we are computing the volume of the solid under the surface. Okay, volume of the solid under the surface. So that is the physical meaning of double integral. But it's not always when there is a question about the double integral, we are always computing the volume. It's not necessarily like that. It depends on the situation. But I would say this one in general, what is actually physical meaning of double integral? That is about volume. Okay, but if the question just say that compute the double integral, so meaning that the result of that computation is actually you are just computation. Okay, there is a kind of example, a kind of question that related to the volume. So that one you will see that volume after you know how to integrate the double integral. So that will be after end of the chapter 3, which is application. So now you know that one of the application of double integral is finding the volume. Okay, actually it is not only volume, but I will explain that later. Okay, that's the general idea, what is actually you are computing or what can you have from the double integral. Okay,